It's like mirrored on my end. I don't know.
No, don't even,
okay.
you should be looking here
I'm looking there.
and the people.
Exactly. Yeah.
Just forget it.
Good.
Do you need a person to be like Vanna White and just like make your slides go?
No, I'll take care of it because I got a lot of sliding to do. So,
Okay, you have sliding to do. Okay,
Yeah.
you have your skateboard.
Yeah, I made this one note. Some of the slides just come on one.
Okay.
But this will work out. All right. So what happens when you have an alignment is it gives you a scheme. It tells you how I'm going to transform one word into another in an efficient way. And our moves that we're allowed to do are called indel mutations. So the in standing for insertion, so I can insert new letters into the word, or del for deletion, I can delete letters, extra letters I don't like. And so, for example, I start with cagtagta, the X word. So I had these three letters I want to get rid of. The AC and the A is sort of in the middle there. So the first move I could do, I could say insert a blue letter, G. That's getting me closer to the Y word. We can also delete letters we don't like. So I deleted this A in the second step, and so on, right? So we're going to do a sequence of these insertions and deletions, and eventually it turns into the other word. All right. So you might imagine situations where you want to do this, like find alignments between words. Generally speaking, in the kind of literature on this stuff, usually you care about finding an optimal alignment. You want to find what is the best way I can line up these two words together. Which is completely different from the questions that we're going to be asking today in this lecture. But yeah, so for example, gene and protein comparison is sort of where this originally showed up. So that's why I picked that example. We can also use this in sort of detecting plagiarism, like see how many edits does it take to turn this sort of sequence of letters into some other sequence that could be useful for some reason. I don't know. I look at all these and I think, oh, yeah, I could make a lot of money if I sort of discovered this first. Yeah, so the problem that I'm going to be talking about today is more about this looking at the sequence of transformations that you can do. So after you fixed your alignment, sort of what is this sort of space of sort of transformations that have been performed to turn the word X into the word Y? This was actually originally thought up by Curtis Greene to kind of look at this kind of from this point of view. He made this simplifying assumption where he's going to say, I'm going to take the trivial alignment. So I'm going to turn all the letters in the X word into the Y word. So yeah, so here's the kind of generic setup. We're going to transform the word X1 through XM into the word Y1 through YN. And we're going to do this by deleting every letter, every X letter, and inserting every Y letter. So there's no alignment whatsoever. Another assumption that we need to make in order to make this nice, the math work out, is we want all the letters actually to be different from each other. So now we're getting maybe pretty far away from the gene example. All the letters in X and all the letters in Y are distinct. We'll talk a little bit about when they're not distinct. But yeah, I'm going to be thinking about that. All right, so that forms what's called the shuffle lattice, right? If I look at all of these different possible intermediate words that I can get from the X word to the Y word using these indel mutations. So for example, starting with X1 here at the bottom, I could just delete that letter X1, I get the empty word. All right, so you always get the empty word as kind of an intermediate possible step. But I could also insert Y letters. And here I have two letters, Y1 and Y2, that I can optionally insert. And I have different choices of where to put them, right, relative to the X1. So I get multiple options here. If I start with, say, X1, Y1, I can still delete the X1 and get Y1 by itself. Or I could insert the Y2. And here, if I insert the Y2, it has to come up after the Y1, right? So I want to maintain the relative order of the Y letters. This is kind of the key idea. But relative, the X's and Y's can be shuffled together however you want. So that's where the name shuffle lattice is from. So
I have a question.
Yes,
Is that poset self-dual?
it is. I don't think so. Actually, I forgot to look this up, but I think it's not self-dual in general.
Okay.
Yeah, but that's a great question. Well, it does have this other property that is rank symmetric, and we'll talk about that in a little bit. But I actually think it's rank self-dual. I should have looked that up. Yeah. All right. So yeah. So this is called the shuffle lattice. And yeah, so this is Greene's original definition in the 80s, and then there were some variations on this that was considered after that. So like, for example, what if you allow repeated letters? What if you restrict, so you don't consider arbitrary subwords that you're shuffling together? You can also mix symmetric functions into this somehow. do this kind of different enumerative things with this. I'm going to mostly be talking about Greene's originally formulation here. Yeah, so S of m comma n, this will be defined to be the set of possible shuffles of a subword of the x word with a subword of y. These are all the intermediate products we can produce. So for example, this word here, y1, y3, x1, y4, x2, that would be in the shuffle, a shuffle word of, between the x1, x2, and y1 through y4. How do I find that? Well, I just pick any subword of x's. Here, I just put both of them. I could take any subword of the y's. Here, I just drop the y2. And then you just, I imagine like I have my y stack, my x stack, and I just kind of shuffle them together so they form one stack or one word. Right. So that is the objects, and then the ordering, of course, is just given by, well, the covering relations are defined by this insertion and deletion. So either, if I want to move up in the poset, so I'll say u arrows v means I'm going up one step. Either I'm inserting a y in there in a place where it's allowed, or I'm deleting an x to go from u to v. Okay. And then the order in general, of course, is going to be a linear extension. Transitive closure. Sorry, of this relation. Any questions so far? All right, so that's the shuffle lattice. Now, some facts about the shuffle lattice, they're not too hard to see, is that first of all, it's graded, right? So this is saying that every maximal chain has the same length, right? Well, if I'm doing a maximal chain here, well, I have to delete all the x's at some point. I have to insert all the y's. So you can see that the length of the maximal chain is going to be n plus n, right? The number of letters in x's, number of letters in y's together. All right, so that's not too bad. And so once you have a graded lattice, then you could ask about how many elements there are in each rank and see if there's any interesting pattern there. This one is known to be rank symmetric. That means that the number of elements at, say, at rank 1 here, the number of elements at rank n plus n minus 1. Or kind of in general, you're going to see this palindromicity to this sequence of rank sizes. So here I see 1, 5, 5, 1. And that also, it's a unimodal sequence. So we're going to be increasing up to the middle rank and then decreasing after that point. All right, so I guess the m equals 1, n equals 2 example is a little too small. If I do this both equal to 2, then you see rank sizes of 1, 8, 15, 8, 1. So 33 elements in total. All right, so that's first fact, and we'll talk about why that's true later. There's a symmetric Boolean decomposition actually of this lattice. It's known, and from that you can derive both of these statements, rank symmetry and unimodality. Second fact is it's a lattice. So the name is not misnomer. It is actually truly a lattice. By a lattice here, I mean that for any two shuffle words, I can find a join, which is just the unique sort of smallest element above those two elements, and a meet, right? The unique biggest element is less than the two elements. So joins and meets exist. All right, so that's part one. And then part two, this is going to be the bubble lattice. This is the new thing that Henri and I introduced. Basically, we revisited the shuffle lattice and said, well, what if we insert one additional move in here? So again, we're going to have the poset is going to be on the same objects. So I'm going to have shuffle words. And we're going to still have those insertion and deletion relations, but I'm going to add in some extra relations here. I'm going to say that if I have two shuffle words u and v, then I have a new arrow, a double arrow. I'll let u double arrows v if I can get from u to v by just doing a transposition move. So now I'm allowed to, if I have an x and a y right next to each other, allowed to flip their order. Transposition move. This is actually something that happens like in genetic sequences, by the way. So you can there's certain mutations called like transposition mutations where you think of like if you want to read what's going on in the gene, you have to like splice it first, or you like extract the component you want, and then you put it back in. And sometimes you put it back in the wrong order. And so this is something that actually happens. Yeah, so this is our move. But here, actually, we want it to be in a particular order. So I want the x before the y. And then if I do the transposition where y goes before the x, that means I'm going up in the poset. All right, now the bubble lattice is going to be just the transitive closure of these combined relations. So I have some indel relations and some transposition relations, and I can combine them in whatever order I want to. Here I just show some kind of random ordering of single arrows and double arrows, but you can do whatever you want there. Okay, and here's a picture of the bubble lattice. So one thing that might stand out immediately is that, well, this is not graded anymore, so it seems like we've lost the combinatorics, right? Because, well, if I say go on the left side of this picture, there's a whole bunch of relations that I have to follow. Also, I didn't put all of the arrows in here anymore. I removed the arrows which are redundant. Yeah, that's a comment that I think I made down here. Yeah, we removed the redundant arrow. So if an arrow is a consequence of some combination of insertions and transpositions together, then we just don't draw it. So we're only drawing the sort of Hasse diagram of this resulting poset that we get. So some of the indels are still essential and some of them are no longer essential. So for example, going from x1 to y2, x2, I got from inserting a y2, but actually that's a consequence of inserting a y2 on the right side of x1 and then doing a transposition after that. So we don't draw that here. Okay. All right. So not graded, yeah, because we can see a chain of length 5 on one side. We see still a chain of length 3 on the other side. If I just delete all the x's to get to the empty word and then insert all the y's, that's always going to take n plus n steps to do that. So this is not going to be graded. So let's see some other sort of combinatorial feature that stands out about this example. So if it's not graded anymore, what we might do is count something. Might say counts arrows either going in or out. And something that you should notice is that, well, if I look at each element here, the number of arrows going in plus the number of arrows going out is always the same. It's always equal to 3 in this example. It's always going to be m plus n in general. So that's a fact that somehow I didn't put on this slide. But yeah, so that's something that I'm going to explain away in just a moment. So there's this regularity to this lattice. Interesting. Oh, also it's a lattice. Yeah, that's another fact. I'll say that. So it has this similar enumerative feature. We lose gradedness, but we get this like Hasse regularity, a regularity to the Hasse diagram, and yeah, it's still lattice. So, but a different one structure. Any questions so far?
If you get rid of the maximal element, is it graded then?
If I
Probably not.
No, we still gotta. Yeah, I think there's still problems to like even some. Yeah, like there's gonna be some.
Yeah.
Yeah, there's a pentagon on the left.
Oh, now I see the pentagon. Thank you. Thank you.
That's right. Yeah. So, but there's gonna be some like pentagon faces, some square faces. Yeah, it's actually like a facial structure to this, and that's something that might also. It looks sort of like a polytope. Comment about that too. Sorry.
Do you have other faces than pentagons?
No. So yeah. So actually, this will only have so the two-dimensional faces are only pentagons and squares. All right. So we're going to explain away this kind of facial structure to it. Also, this Hasse regularity using a simplicial complex. So here's this simplicial complex that we can define. This maybe looks a little bit confusing at first. So first of all, yeah, basically what I like to think about is I'm defining a simplicial complex where I'm looking at subgraphs of a complete graph, a complete bipartite graph. Right? So I have these two parts. I have the x words. The x letters are going to be like vertices and one of the colors I drew in red. The other color class are the y letters, y1 through yn. So I also add these two new letters, add x0 and a y0. So that's something else we do. And yeah, so we're looking at the complete graph, complete bipartite graph, and we're looking at certain subgraphs of this to get this complex. The other thing is I also have to add loops. Right, so it's like a complete bipartite graph, except I would add loops at all the vertices. Weird thing to do. Right, so yeah, so we have the loops. That's part of the ground set. We also have the edges between x's and y's. But we have this restriction that so we don't want to consider any the x0 or the y0 loop. We throw that out. Also for the edges, I don't want both the x0 and y0 together, but I'm allowed to do x0 to y1 or y2. Yeah, so you can mix x0 with a non-zero line. All right, so that's the ground set of the complex, and then we're just going to take collections of these edges that we can draw kind of in this rectangular strip without any crossings that happen here. So So for example, here would be a collection of non-crossing loops and edges that I could do. Here's what I mean by crossing. So if I have two edges, they're considered crossing if their sort of interiors are crossing, like they're allowed to have the same endpoints, but they can't sort of run through each other within the rectangular strip. Also, for loops, that means that I'm not allowed to have another edge that includes that endpoint. So if I have the X loop, I'm not allowed to include the edge that includes that same letter. All right, so that's my complex. And we're going to consider the abstract simplicial complex, whose spaces are these non-crossing subsets of this collection of loops and edges. And here's an example of this complex when, again, so same parameters as before. So m equals 1, n equals 2. I do have to throw on these x0 and y0 letters. So you see them showing up in some of these elements of the ground set. And what do we do? So we just draw. So the simplicial complex just means that I draw the ground sets, which had 8 elements in it, and then we draw an edge between two things if they're compatible. So if they're non-crossing with each other, and then we take the complete complex of this thing. So fill in all those triangles. And it turns out there's no higher dimensional faces in this case. So I have some vertices, some edges, some triangles. That's it. Looks roughly spherical. Right? Looks like we're the picture looks roughly spherical. Also, if we just enumerate, right, we can just count. There's 8 vertices, 18 edges, and 12 triangles. So right order characteristic be a sphere. So that looks good. And yes, this is something that we proved. It's shellable, pseudo-manifold, homomorphic to a sphere of the appropriate dimension. N plus n minus 1. Okay, so what does this complex have to do with the bubble lattice? Well, it's really kind of dual in some sense. So the maximal faces, so these triangle faces in this complex, those are in one-to-one correspondence with the elements of the bubble lattice. And the cover relations also in the bubble lattice is sort of seeing when I have adjacent facets, adjacent triangles in the complex. Okay, so we can maybe convince ourselves by looking at this picture that they sort of look dual to each other, kind of polar dual pictures in some sense. And actually, this correspondence is not too hard to work out. So yeah, so here's how it goes. So I'm going to say, all right, so given a shuffle word, so an element of the bubble lattice, I'm going to associate to it some n plus n tuple of the set of edges and loops. And oh yeah, okay, so I was going to do an example. All right, so how do we do that? So I'm going to give you this word shuffle. So we have some y's and some x's. Yeah, so here's what we do. We look to the left of each letter. So I'm going to look at the y1, and you look to its left, and you don't see anything there. That means I'm going to connect y1 to x0. So you see we have this edge going between y1 and x0 in this picture over here. And then we do the same thing with the next letter. So x2, I look to its left, and I look for the first y letter on its left. That's what we have to do, right? So I see the x2 points to the y1. So that's why I have an edge between y1 and x2. The x3, I look to its left, it sees an x, I don't like that, so I keep going until I run into a y, and it sees a y1, so that means I have the y1 x3 edge. And so on, we keep doing this, so I'm going to connect y2 to x3, right? That's the first x letter it sees to its left, y4, x to x3, and then x4 to y4. And that gives me all the edges, right, in the picture. And then we put loops at any letter that was not present in the word shuffle, right? So the y1 or the x1 wasn't present and the y3 wasn't present, so I put loops there, right? And yeah, we can kind of convince ourselves, I guess, from this picture that yeah, we just rearrange these letters just with these green arrows turn into edges, then it'll be non-crossing. So yeah, so it's something that we proved that this is a bijection between the maximal faces of this simplicial complex and the shuffle words, and it's a bijection that actually it induces a bijection on the edges in a Hasse diagram to adjacent pairs of adjacent facets in the complex. So it's sort of sending the cover relations correspond to like edges in the dual graph. The complex. Irregular. This means that the bubble lattice is Hasse regular. So this is like a really roundabout way to say that the bubble lattice is Hasse regular. That's just witnessing this sort of thinness of the simplicial complex. That means something. An open question, which maybe now actually is closed. I don't know. Is this a polytope? Is known already for some of these n or n's, something called a Hochschild polytope that was produced not very long ago. And Joseph Doolittle, by private communication, says that he has a construction for, in general, M and N as a polytope. So as a convex whole of minus points. So that's all I have to say about that. Any questions on bubble stuff? Good. So let's move into part 3. So now we get to the theory part. So I'm going to talk a little bit about this semi-distributivity condition. This is an interesting feature of the bubble lattice. It's a distinguished feature. But first of all, before I do semi-distributive, I remind you about what is distributive. So we say a lattice is distributive. So for a lattice, you can think of it as you have these two operations, right? Meet and join. And you could say, can I distribute a join across a meet of two elements? Or dually, can I distribute the meets across a join of two elements? Turns out these are, if I know that one distributive law holds and the other one holds for free, they're sort of only if, or we just stated that they're both true or not true. That's the distributivity law. Right? It's kind of the familiar law, except now with meets and joins as our operations. Classic example of something that's not distributed. Would be this weak order type A2. So here, if I take these two elements as my X and Y, and then this one over here is the Z, you just see that it doesn't work, right? Distributivity law fails, right? If I do the meet of X and Y and Z, I get to the bottom element, join that with X, I get down to the X. Whereas if I do joins with X with each of the elements individually, I either get to the Y or I get to the top element, and their meet is Y. So so I get not equal. So not distributive. It is, however, semi-distributive. So this is a very nice theorem. It says the weak order of any Coxeter system is a semi-distributive lattice. It should say any finite Coxeter system, semi-distributive lattice. So semi-distributive, what is that? So semi-distributive means that distributive happens, but only sometimes. That's the way I like to think about it. Basically, I say, I want to enforce the distributivity law under the condition, so with same X by Z, but under the condition that if I have the join of X and Y is equal to the join of X and Z, then I want to make sure that the join of X across the meet of Y and Z is, has the distributive law hold there. So what would I get when I apply distributivity? I would get X join Y, and then there's sort of like another case like this, and then meet that, meet that with X join Z. But if X join Y and X join Z are the same, then I can just replace that with just one of them. So that's why we write it this way. And the dual law as well. And this actually, for semi-distributivity, these two conditions are not equivalent to each other. So if I just know one of them, it's called joint semi-distributivity, and the other one we call meet semi-distributivity, and they're not equivalent. So one could hold while the other one doesn't.
Yeah, the example you have up there, is that semi-distributive?
That one is semi-distributive, yeah.
Okay.
If I take the same X, Y, Z, you'll see that it doesn't satisfy the initial condition, right? So it only, it's only distributivity sometimes, and that sometimes doesn't include this case, right? Because if I do, let's see, X join Y and X join Z, I get to two different places. X join Y is just Y, X join Z is the top element. So I don't enforce a distributivity condition in that case. And it turns out that, any of the cases where I do require it, this will work out. Classic example of something not semi-distributive is the partition lattice. So if you like partitions, too bad, not semi-distributive. In fact, semi-distributive lattice implies the Mobius function can only take values in the set plus minus 1 to 0. It's actually very restrictive with what kind of lattices are permitted there. And here with partition lattice, of course, you have very large Mobius function values that will show up somewhere. So that one's no good. Nevertheless, there are many interesting examples of semi-distributive lattices that show up, which is why I'm interested in them. So the original one is free lattices. If you have any familiarity with free groups, it's kind of like that. Right, so free group, you think of it as like, I have a group generated by some set, and I just look at all possible words, expressions I can write, and then apply like associativity, yada, yada. With free lattices, same idea. So I just take a set of elements, I want to take the class generated by that, so I'm looking at all possible words I can write down in these joins and meets operations, so combining them together. But you also have to apply like the lattice axioms and just take the freest thing that you can get. Surprisingly, so free things you usually think of, they don't have any properties, or it's like it's just the most generic possible thing. However, this one actually turns out to be semi-distributive, so it's distributive in the right places, which is kind of confusing to me. Anyway, I don't usually think about free lattices, but the other ones I do like. So there's the weak order on Foxter systems. You have to make it finite so that you have actually a top element you can get to. Tamari lattice. And lots of variations on the Tamari lattice are very interesting. So this is like, so Tamari lattice is ordering on certain Catalan objects, so like Catalan numbers. Just kind of a lattice theoretic interpretation of what's going on there. There's also a generalization of that called Cambrian lattices. Nathan Reading introduced. So these are all semi-distributive. There's also a large generalization of all of these examples of lattices of torsion classes. Maybe not including free lattices, but the other ones, so there's lattices of torsion classes and that would be semi-distributive, and lots of things you can think of as torsion classes. I'm going to talk about that a little bit. All right, so here's our theorem: is that bubble lattice is also on the list. Okay, so you can join these. All right, so so now I want to talk about torsion pairs. We're gonna so I know some people in this audience knows a lot about the subject. And I don't know, so maybe they talked about this. But I'm just gonna kind of briefly go through the sort of ideas here. I don't want to go too deep into this. Okay, so what I want to do is I want to say that there's a certain kind of collection of semi-distributive lattices that are sort of representable in some nice way. So you can represent them as lattices of torsion pairs. And here's the setup, just quick and dirty setup for this. So I take a finite dimensional associative algebra. I guess it just over some field doesn't really need to be complex numbers. And we want to consider the category of finite dimensional left A modules. So that means something to you, okay? Right, so I'm just looking at the finite dimensional representations, basically. That's how I think of this. And then inside of that category, I can split it up into these two subcategories. It's called a torsion pair. So there's like the torsion part, the T part, and there's a free part called F. And the defining condition on a torsion pair is it should be sort of maximal with this orthogonality condition. So the orthogonality of this torsion pair is just saying that if I take any element in the torsion part, any object in the free part, should be null homomorphisms from torsion to free. Which, if you think about kind of like finite abelian groups or something, you have the Z mod n, there's no map from that to Z. That's sort of what's going on there. Okay, once you have these torsion pairs, then you can apply an ordering to it. You can say, torsion pair TF is less than or equal to T prime F prime if there's an inclusion on the torsion part of it. T in T prime, or, and this is equivalent, is that the free part should have an inclusion in the reverse direction. Okay, so this forms a poset. In fact, it's a lattice. So you get a lattice of torsion pairs, and general facts. This lattice of torsion pairs is semi-distributive, something I proved with L. Garber a while ago. And actually, if it's finite, then it's also Hasse regular. I don't know who to cite for this one, Christina. Anyway, these are some facts we know about lattices of torsion classes.
And that's in Yama, right?
Yeah, okay. Yeah. I think there's like a lot of different ways to see this, but there's a connection to, okay, so how do we get Hasse regularity to bubble lattice? We said that, well, there's this simplicial complex that you can sort of associate with it. You can do the same with the torsion classes. So there's this thing called Sportal tilting complex, or there's other complexes you can find. And you can use those to say, apply this sort of same kind of trick. That's going to tell you about this lattice of torsion pairs to be Hasse regular. Now, I would say most, could say in quotes, yeah, like most known lattices that satisfy these two conditions, being semi-distributive and Hasse regular, are some kind of like lattice subtorsion pairs. So that's why I'm talking about it in the slide. Okay, so for example, the Tamari lattice, right? That was on our list of things from the last slide. That's the isomorphic to lattice subtorsion pairs for this the path algebra on this oriented path quiver. This is due to Hugh Thomas, through that one. You can also interpret the weak order for type A, let's say, although you can do other types as well. Weak order, that's lattice subtorsion classes for the pre-projective algebra. So it looks like this. I took the directed path quiver, I then reversed all the arrows, and then applied certain relations. There's actually different choices you can make for these relations. Give you the weak order. All right, so that's another example. You know about that one. There's also this thing called Graspon-Tamari lattice. Lots of people. So I think the second one might be Mizuno. I did that one, and then there were like 8 people who did this last one. Yeah, so a lot of like classic examples, combinatorial examples of semi-distributed lattices that are known to be Hasse regular are really like lattices of torsion pairs. And an observation, I'm just gonna say this, is that the bubble lattice above 2,1 is actually not a lattice of torsion pair. So it still has these properties, right? It's semi-distributive, Hasse regular, and to my knowledge, this is like the only example that's like relatively nice combinatorial example where it's not lattice of torsion classes. And Christina asked me earlier today is why I know that this is true, and my answer was I went to lunch with some representation theory people, showed them this, and they said no, that there's no way to do this with an algebra. So anyway, I'm just kind of quoting them. Yeah. Okay. So then there's this general problem that is sort of related to is okay. So can we sort of put the right characterization of torsion classes? So it's not enough to just be semi-distributive and Hasse regular. What else do we need to add in to say that it's definitely a lattice of torsion pairs of an algebra? It's an interesting question. And this is showing like part of the boundary of that question, maybe. Now, so I said that so the bubble lattice is not a lattice of torsion classes for an algebra, but there's something kind of abstraction of the category, the module category for an algebra that you can use as a replacement to end up getting the bubble lattice. I don't know, saying a lot of words that aren't really fitting together nicely. So there's this sort of abstract framework called factorization systems, which were recently introduced by Reading, Spire, and Thomas. And I'm not going to go through all the details of this because again, we're getting, it's getting a little heavy now. I just wanted to show you an example of a factorization system just to show you what this looks like. So here we're going to, so our setup is we have a set. It looks kind of like a there exists symbol, but it's sort of on its side. Or E, maybe it's like turn on its side. This is a Russian Cyrillic letter character, I think called Sha. They wanted to use the letter S, but they didn't want to reuse an S that's already used. So they used Sha instead. And that's a set. And then we have a relation, arrow relation, which is only assumed to be reflexive. So there's no other assumptions about this arrow, it's just reflexive. So for example, that's example in Greene over here. So I have a set Sha with 3 elements A, B, C. The reflexivity means that A points to A, B points to B, C points to C. And then on top of that, I'm going to say A points to B and B points to C. It's not transitive though. So you don't read this and say, oh, well then A points to C. No, we're not going to assume A points to C. So we'll only have these 5 relations. Okay. So yes, that's our running example. Now, we want to produce something that's like torsion pairs, and from this kind of abstract framework. And so what you do is you define this notion of orthogonality. So if I have a subset X and a subset Y of Sha, you say that you define this thing called the right orthogonal complement and left orthogonal complement. And basically what you do, so if I want to find this orthogonal complement of X, this right perp of X, what I do is I take the objects in Sha for which there's no arrows coming from X into that object. In particular, no element of X can live in X perp, right? Because of the reflexive condition. So this is X perp as at least a subset of the complements of X, but it may be also more restricted than that. So that's called the right perpendicular set, and then you also have a left perpendicular, which is just dual. So instead of saying there's no elements going, no arrows going in, there's no arrows coming out of these X's. Yeah, so you take the objects for which there's no arrows going into a Y. Okay, I just said that in reverse. Anyway, you can see that. I always get this mixed up. Now, from that, you can form this lattice of maximal orthogonal pairs, which they call pairs of arrow. So you take these pairs of sets X and Y, subsets of SHA, which have this property that X is the right perp of Y and Y is, no, I said that backwards. All right, well, anyway, you can see the condition there. Yes, there's a left and right perp. They're perpendicular to each other, just in the way that like the torsion pairs have this kind of perpendicular relation on them. And again, we order these by inclusion of the first component. So we say X, Y less than or equal to X prime, Y prime, if and only if X contained an X prime, and at the same time, Y contained a Y prime. So equivalence. Okay. So in our example, let's just look at what this set of maximal orthogonal pairs is. So it turns out, so I'm looking at a 3-element set, SHA. There's 8 different subsets I can consider, right? Of a 3-element set, two cubed. Only 5 of them are going to be torsion, or like the torsion part, yes, of the maximal orthogonal pair. And in fact, if I just order them by inclusion of the torsion parts, it looks kind of like this. This is just the Tamari lattice on 5 elements. So let's just look at an example of this real quick, maybe like, yeah, so if my torsion part is the C and the complementary part is AB, what this is saying is that there's no arrow that points from C into A and B. And conversely, there's no arrow that points from A, B into C.
No, you have to go backwards.
Oh, yeah. Yeah, that's right. Yeah, so it's this condition that we're checking.
Yeah.
Yeah, maybe the confusing one is this one. So why do we have A and C are maximal orthogonal pair? So it's like there is an arrow from A to B, which means that if I have A in the left set, then I can't put B in the right set. And conversely, there's an arrow from B to C. So if I put C in the right set, then I can't put it in the left set. So this is actually a maximal orthogonal pair. B doesn't have anywhere to go. Go home for B. Okay. So yeah, so here's the theorem that they proved. Basically, if you have a, so I didn't tell you the rest of this. Yeah, if you have, so if additionally you have these other 2 arrows, double head arrow and hook arrow, and if they form what's called a 2-acyclic factorization system, then this poset maximal pairs is semi-distributive. And conversely, so they characterize these finite semi-distributive lattices as those that arise as maximal orthogonal pairs for some 2-acyclic factorization system. And roughly speaking, the conditions on the factorization system, it completely comes from this this kind of representation theory context. Basically, they're saying this arrow relation. Actually, so I kind of say that here. So in the context of if I'm looking at an algebra, I'm looking at lattice of torsion pairs, my set SHA, I'm going to take all of I'm going to take these things called brick modules, which are certain indecomposable modules, okay? And we define an arrow between 2 bricks if there's a non-zero homomorphism between the corresponding modules. Okay? So it's just saying, is there a homomorphism? Is there not a non-zero homomorphism? And that's defining this relation, arrow relation. And then, yeah, show that the 2-acyclic condition holds and factorization system, yeah, whatever. Some other stuff, which is not the key point of the talk. So for example, if I take the directed path quiver, then you get to this, looks like kind of the root posets, say a type A. Or you might see this as an Auslander Brighton quiver. Yeah, a lot of interpretations of that. That's a factorization system. Basically, you're picking out some key part of the module category for the purpose of computed torsion classes. All right, so bubble lattice. I said that this is not less torsion classes, but because of their theorem, because it's semi-distributive, there has to be some factorization system you can write down. And what the student of mine, Jeremy Baxter, found is here's the description. Basically, you take a rectangle. In this case, I just took a square, and then you tack on some additional points that sort of point in or point out of it. And these define some of the arrows, and then you get the normal arrow by just combining these two guys. Oh yes, I didn't say what molt is. So molt just means that first I do a double hit arrow, and then I follow it by a hook arrow, and that means that there's an arrow. So for example, I could go down and then up, and we get an arrow between corresponding objects. And this looks kind of like, if I just took one of these big triangles, like the root poset type A, this looks like I just took part of that and I just removed a few objects from it. And I got the factorization system that defines the bubble lattice. And so this kind of leads to some questions of, well, what other sort of sub-factorization systems of this kind of type A example is still going to give you something which is semi-distributive and Hasse regular. That is I have no idea about. But that's the question that I'm interested in, is sort of characterizing lattice torsion classes sort of abstractly, and using this kind of example of the bubble lattice as a way to see, like, okay, here's a non-example. You can't have this kind of factorization system. So I don't know, this might be an avenue to try to get a characterization. All right. So that's the theory. All right, now we're on to enumeration. And the last few minutes. All right, so we're going to squeeze this in. So Greene proved a lot of enumerative results. Basically, he did all. So he was looking at the shuffle lattice, and there were like certain things, standard things that you compute when I have a graded lattice. Like you want to count how many chains there are. You want to count how many elements are at different ranks. You want to know how many elements are there in total, actually, but it's not super obvious. There's various sort of polynomials that you sort of evaluate, characteristic polynomial and so on. And he did all of them. Yeah, so he kind of did everything. There was also this paper by Simeon and Stanley where they, I would say, like took a more sort of algebraic approach where they sort of interpreted things that Greene was doing as you have like the symmetric group acting on the maximal chains, and then they computed that representation and showed some stuff. Anyway, so yeah, that was very interesting. Let me just walk you through one thing that Greene proved, which is just how many elements are there in this, how many shuffle words are there? So there's a not too difficult formula that you can get by just saying, all right, if I want to form a shuffle word, I just take a subword of the X word, I take a subword of the Y's, and then I just have to ask, how many ways are there to shuffle them together, some binomial coefficient. This gives me a two-dimensional sum. I choose an X, the size of the X word, size of the Y subword, and then I count how many ways there are to shuffle them together. What's interesting maybe about this formula is that it's a one-dimensional sum instead, right? So there's actually a single parameter version of, there's the sum that only depends on one parameter. What you do is you choose a k element subword of X, k element subword of Y, and then you have this power of 2 where you sort of fill in the rest of the word with some X's and Y's in some regular way. Let's do that. Let's look at his proof of this. So I want to get rid of the formula just yet. So I want to count how many words there are, and I'm going to do this with this restriction. I'm going to count how many have k incoming double arrows, right? Because we want to use, we have the sum here, so I want to divide this into cases. This parameter k is going to tell me how many double arrows are pointed into the word. Considering, remember, double arrows means transposition. So I'm saying how many transposition moves I can undo here. So it means we want exactly k consecutive subwords where I have a y followed by an x. Sort of. So my word W is going to have these pairs, right? Y followed by an X, Y followed by an X. And so you have some Y's, some X's in there. And you can see that, if I just choose what Y letters show up, is M choose K of those. If I want to choose which X letters show up, it's N choose K of those. And so once I know which letters appear, they have to be sort of sorted in a unique way, right? Because I need the X letters to appear in order. So XS1 appears before XS2 or XS3 and so on. The Y's have to appear in the correct order as well, relative to themselves. So that means that once I've chosen these two subwords, then that's, there's only one way to fit them together. And the rest of the word, you can just fill in by just choosing a subset of what remaining letters you want to appear. So, if I say I want certain X's to appear and certain Y's to appear, I don't want them to have this property where a Y comes immediately before an X. So there's a unique way to fill them in as the rest of the word, right? So in between, say like this XS1 and YT2, if I don't want to see Y followed by an X, then I have to start with a bunch of X's, this dot part, and then finish with Y's. That'll be the only way to fit those extra letters in there. And yeah, so once I've determined what other letters appear, then there's only one way to put them in, and that's why we have this power two. So choose a subset of the remaining letters, and there's n plus n minus 2k letters left. So I've used up 2k letters so far.
So is this like Curtis prove it or?
This is Curtis proof.
Okay.
He didn't have the double arrows because he didn't need them.
Okay. Yeah.
But basically, yeah, that was his proof. Yeah, very nice. And this proof is actually the key to like all of the enumerative stuff he did in the paper. So finding characters of polynomial, finding counting chains, things like that. Okay, I also put this example in here. Let's try to illustrate this. I don't know. I wrote these slides a while ago, so I forgot why I wanted this example. But okay. Any questions so far? Yeah. All right, I guess I was just showing here. Okay, so I choose x1, x3, and y2, y3 is y4. So this is like k equals 2 k's. Choose 2 of each of the x's and y's, and then it tells me the y2 goes for x1, y4 for x3. That's the way I have to sort them. And then I choose what other letters I want to throw in. Let's say I want to throw in the x2 and the y3. There's a unique place that they can go, right? The x2 has to go in between the x1 and x3. Had to go here. The y3 had to go between y2 and y4. Had to go there. And it has to go after the x2. Okay. So now if we just modify this a little bit, we could count the number of words of in degree k. And in fact, we could do something more refined. We could say how many words there are with k1 incoming single arrows and k2 incoming double arrows. And yeah, basically the same argument is going to say, all right, well, we just counted how many double arrows are going in, and now instead of a power of 2, since I've only counted the ones with k1 single arrows coming in, it's going to be this polynomial coefficients. Not too difficult. All right. Also, this is after we've done arrows. I think I just put this example just to show you that I took the time to do the n equals 2 example. Looks sort of impressive. I don't know. This is supposed to be a polytope in 4 dimensions. Yeah, can't really see it very well. If you're experienced with that, maybe you know. All right. So connection between bubble lattice and shuffle lattice, enumerative connection that we get is that actually, if I look at the number of elements, so if I take a single word, shuffle word, the in degree, so the number of arrows pointing in to that word and the bubble lattice is equal to the rank of that element in the shuffle lattice. And so, since we just counted sort of number of words with a certain in degree, we also get then the number of words at rank k in the shuffle lattice. And that was something that Greene did. So we recovered his formula. And there were a lot of other things that he did that we didn't do, but we were coming from the perspective where we actually cared about sort of keeping track of both these two different types of arrows. We wanted to count them separately because we're interested in these polynomials called Chapeton triangles. Okay, this is the last slide. Oh, yeah, okay. Hopefully this is okay. So yeah, so we're looking at these called Chapeton triangles. So yeah, let me define this real quick. So there's 3 polynomials. So Chapeton triangles, this refers to, you have an H, kind of analog of the H polynomial, H of A, B. You have an analog of the F polynomial of some complex of F of A, B, and then there's an analog of the M polynomial. Sorry, the characteristic polynomial, or the Mobius polynomial of M of A, B. So with The H polynomial, we define it using the bubble lattice, and we just ask for, look at each word, ask for what's in degree, and then this in sub arrow means I only count the single arrows, I don't count the double arrows for that statistic. So for example, in this example here, let's see, okay. In the example, we have H of AB. Well, we have one element that has no in degree at all, right? That's the bottom element. So that would be A to the 0 times B to the 0. We have 3 elements which have in degree 1, and that's a single arrow. So we have 3AB. We have 2 elements which are in degree 2, but only one. No, sorry, in degree 1 and. Yeah, so in degree is 1, but it's a double arrow going in, so there's no B's that show up. And then there's other terms. Just in the interest of time, I'm just gonna skip over that. But that's the H polynomial, and actually we proved this this formula, right? This basically follows from the previous slide, where we're counting sort of elements with certain in degrees. This is the polynomial version of that. And Curtis Greene, he observed this, but just in the restricted version where we didn't separate the 2 different types of arrows. This is the rank generating polynomial for the Sheffield class. All right, so that's our first polynomial. The second one is F, which is defined in a quite a bit different way. We look at instead this complex, right, the non-crossing bipartite complex that we had way back in section 2. So we have these loops and edges. And what we do is we say, all right, we're going to take the basically F polynomial for this complex, except I have these 2 different types of elements in my ground set. And I'm just going to count them differently. So one parameter, the C, is keeping track of the edges in my set, and the other parameter D is keeping track of the loops that it sees. All right. So I'm not going to do more examples. Yeah, so this is the complex again, and yeah, so we just count faces in different dimensions. Except we separate out these 2 different types of elements in the ground set. And the third polynomial is this Mobius polynomial. And what this means is you look at all the intervals of your shuffle lattice. So here we're looking at the shuffle lattice, our third structure. And we say, all right, so look at all the intervals, U to V. You take the Mobius function value there. So if you know Mobius functions, Mobius function right over. Right, so it's just defined by this condition. You do W, where W goes between U and V. This is equal to either 1 if U equals V, or 0 otherwise. So that's the quickest definition of Mobius function I can come up with. Right, so yeah, so this is called the Mobius polynomial. And the surprise is that these polynomials are related. So they're kind of defined using different statistics on these like different objects that are connected to each other, right? Shuffle lattice, bubble lattice, and this non-crossing bipartite complex. They're all sort of related to each other, but we're sort of counting different things. They're different polynomials that you get, but they're related by these birational transformations, conjecturally anyway. So the first one that we know, so we can do the connection between H and F. That's not too bad. We still don't know the other one. So between M and H or F and M, they're both possibilities. But that's what we have conjectured. So like help in figuring that out. So if you know anything about characteristic polynomials, Mobius functions, whatever, or anything else, please help. The real surprise about this, though, is that these are the exact same birational transformations that show up in 2 other settings. So the first one was Oxford-Catalan combinatorics. This is actually how Schopenhauer's name gets attached to this. Is that he just sort of came up with these polynomials corresponding to these like kind of clustery things, Oxford-Catalan numbers, and he's proved his conjectures were proved by various people. Also showed up in this work that I did with Algarve on grid Catalan combinatorics, and now on shuffle words, and so. Question that I have is basically, is there some kind of unifying theory to this, like a unifying way to set up these polynomials and say, when should these relations hold? All right, and sorry for going over time, I'm going to stop here.
there any more questions for Thomas or comments?
I have many questions about factorization things. Can you distinguish between, so you're getting, you can start with like a torsion class, or essentially, or with torsion category, whatever, set of torsion. Torsion lattice. So you essentially get like an AR quiver.
Yes.
Can you distinguish between the injections and surjections? It looks like
Yes,
when
yeah,
you're
so
drawing
that's essentially what this double hit arrow and single and the hook arrow are. Is it's I think it's not exactly that. They're not exactly the same as injections and surjections, and I can't remember what the difference is.
So like,
But it's essentially the same.
what I really want to do there is I want to like get an intrinsic characterization of torsion classes by saying that they're closed under extensions and quotients. Because like, if we know what the surjections are here, and like we can maybe sort of see what extensions, again, we have some of the AR quiver, we only have the tau ridges. Like,
Yeah.
is there something like that?
I don't know. Yeah, I'm not sure. Yeah, so what I should say is like part of the definition of factorization system is it says if you start with this, just the ordinary arrow, it defines for you a double hit arrow and a hook arrow. And then conversely, if you have double hit arrow and hook arrow, that they have to be reflexive and transitive. You can define a single arrow from that. And to be a factorization system means that if you go in both directions, you get back to where you started. So if I start with a single arrow and I do this back thing to split it up into these two different types of arrows, which is basically it's like sub relations. So you know the double hit arrow is saying certain arrows are maintained, the ones that are sort of behave like epimorphisms in a sort of categorical sense, which is usually basically the same thing as surjections, and dually for the hook arrow. And then to go, if I have that pair, the double hit arrow, the hook arrow, then I can glue them together, do the bolt operation to produce arrow. And if I get back to the original arrow I started with, then you call it a factorization system. Okay, so that's kind of like that's baked into the definition. Yeah, now I've lost if I'm getting any closer to answering your question. Yeah. So you were saying. I don't know. Maybe we'll have to talk about this.
Sure.
Any other questions or comments?
How do you prove semi distribution of the bubble lattice? Just directly or?
Yeah, actually, we basically just do it directly. It's not too bad, it turns out. So yeah, so for this to actually write down what the join and meet operations are is not too complicated for this example. Usually with like for say the smart lattice, what you do is you define like a closure operation on positive roots and then use that to define the lattice. And here yeah, I think you could do that sort of closure operation method, or you can just actually like fairly directly give a formula. Like if I give you two shuffle words, then you can find what the join has to be. Basically, you want to look at like what's you know, so if I have certain Y letters here, like you can figure out what the supports of those words have to be, and then you see like, okay, is there a consistent way that I can include the X letters, and if not, then you have to delete them. Yeah, that's basically it. And once you have that formula, then you can use that to get some distributivity. That's one way to go about it. You can also like identify the joining reducibles and use kind of some more like theoretical tools to prove semi-distributivity, like kind of like local proof of semi-distributivity to apply like a global semi-distributivity. There's various approaches that are possible, but I think like the cleanest one is just do it directly, which is sort of surprising because usually these things like they sort of resist like direct approaches. Yeah.
Anything else? Well, let's thank Thomas again. So as a reminder, we're here again on Friday for a double header, 1 o'clock.
It's this way.
Did you do any more?
I've done, I posted stuff to you. It's my parents. So,
No.
I can post this again, but middle of the week, but I think that I'm starting on the next section. I could probably post it back up there.